Throughout the rest of this chapter, A sub n is going to represent our original series, like our original problem. B sub n is going to represent our comparison series. So that's the notation we're going to use. Now, you know, like 1 over n cubed, that's a convergent P series. But 1 over n cubed plus 1, that's no longer a P series. This example we're going to do, this is certainly not a P series. It's not just 1 over n raised to a number, right? Or a number over n raised to a number. So what we're going to need to do, we're going to basically take harder looking series. This is actually something really simple, though. You're going to like this test, but we're going to take harder looking series and we're going to compare them to the easier series that we already know what it does. So your comparison series is something kind of easy, straightforward, where you know what it does pretty quickly. All right. It's a lot of times it'll be an easy P series. It doesn't have to be, though. It could be a geometric series. It could be, maybe a basic integral test or something like that. But it is something that you know what it does and why relatively simply. And then we'll compare that to a harder looking series. So here's our nice, neat, colorful steps for the limit comparison test. You typically will use it on problems like these with rational functions, with polynomials. Notice if I do limit as n approaches infinity of this thing in my head, trying to apply that nth term test, that limit is equal to 0, which means that nth term test is inconclusive. But it works really well when you have polynomial, like polynomial or polynomials, the rational functions, and also if you even have like radicals and stuff like that, things we've done limits of, that's where the limit comparison test can work really well. So here's how it's going to work. Given an original series, you're going to find a comparison series, and I'll tell you a couple tricks of how to do that. And then you're going to write that down, and then you're going to write down what that does and why. So you're going to always write down your comparison series, and you're going to tell me, hey, that's a convergent P series, that's a divergent geometric series, that's a convergent integral series. So write down what that does and why. And then what we'll do, we're going to take the limit as n approaches infinity of the original series divided by the comparison one. So you got to show me what you're taking the limit of. And if you get that limit is equal to L, L is going to represent a finite positive number. So if you take this limit of the original problem divided by the comparison series, if you get a finite positive number, that means both series do the same thing. So you're both going to converge or both going to diverge. All right. And then if you don't get a finite positive number, that means your test is inconclusive, which means either the limit comparison test does not work. I might have to go to a direct comparison or a different test, or it also means that you may have chosen incorrectly for that comparison series. Now, finite, you know what finite means. It means it's not infinity, right? And then positive, you know what positive means right there. So finite positive number is what you're looking for. One technique when we have polynomial over polynomials like this, one technique when I'm finding the comparison series, and I'll give you a few other examples after this example, but one technique is just to look at the highest degrees and subtract the highest exponent. So when I look at this, I see n to the first over n to the second. And when you're doing the limit comparison, the coefficients don't matter. If I'm doing a direct comparison, I want the comparison series to look as closely as I possibly can get it to the original problem. But when I do the limit comparison, I don't care. All I care about is n over n squared, the highest degrees. N over n squared, that will give us 1 over n. So 1 over n is my comparison series. That's my B sub n. So I'm just going to write that down. And then I know that this is an easy P series where that P is equal to 1. So I got that easy P series. This is a divergent P series. So I'm following the steps there. So I have my comparison series, and then I wrote down what that does and why. That's a divergent P series. And now I'm on this step here. We're going to take the limit as n approaches infinity of the original A sub n, the original series, over the comparison series. So again, the original series, that's my A sub n, and that comparison series, that's my B sub n. So let's go ahead. Let's go right to it. We're going to do a limit as n approaches infinity. I'm going to take the original series. There's my A sub n. And I'm going to divide that by the comparison series, the 1 over n. It'll also work if you chose 5n over n squared and you chose 5 over n. You're still going to have a divergent P series. You could have a 5 over n right there. We're still going to get the same answer at the end of this one, but I'm telling you the coefficients don't matter when you're doing a limit comparison test. All right, so show me what you're taking the limit of, all right? And that's why when we do the nth term test, you're doing the limit as an approach infinity of the original term. When we're doing the limit comparison test, it's the original divided by the comparison. So you always have to show me what you're taking the limit of. And then when here, we're just doing some basic algebra now. All right, so now we have the limit as n approaches infinity. Remember, when you divide fractions, you're just gonna go ahead and multiply by the reciprocal. So that's going to be times like an n over 1. And now you're looking at the highest degrees on the top and the bottom, right? So if you have 5n minus 3 times that n, you have 5n squared followed by some stuff you don't care about over n squared followed by some stuff you don't care about. So when we're doing that limit as n approaches infinity, we can use our pre-calc shortcuts. Now, our degrees are the same on the top and the bottom, so this limit answer is equal to 5. All right, now let's remember what we're looking for here, okay? So if I get 5, that is a finite positive number. It's not infinity, and it is a positive number. Now, don't get so excited that you got that finite positive number and you're just going to say converge right away, all right? The reason we compare it to this, that means both series do the same thing. Either they're both going to converge or they're both going to diverge. And if you follow those steps, like I showed you don't have any thinking to do at the end of this problem because you already have it right here in front of your face. So since this comparison series diverge, that means the original series will also diverge. So you got to tell me converge or diverge, and then tell me that the test that you're using, this is our limit comparison test. Limit comparison. So just write that down. Remember, there is no such test called a limit test. If you put limit test, that's a big deduction. I'm going to count that wrong, all right? There's the nth term test. There's a limit comparison test. We're going to do something in the future what also involves limits. There is no such test called a limit test, right? But there is a test called limit comparison. Don't put LC. I'm not going to know what that means there. We don't like that anyways, all right? So the diverge limit comparison, there's our final answer there. Now, that's an example of your limit comparison test. The next video, we're going to do the direct comparison test. And then sometimes the choice is, oh, I'm not sure when to use which one. I'm just going to tell you, we'll talk more about that later on after we learn all of them and once you get experience working with all of them. But the limit comparison test works really well when you have polynomial stuff going on top and the bottom, or even if you have radicals and stuff on the top and bottom. Although if you have radicals, sometimes the direct comparison test might work as well. One thing that I just want to mention of how to find the comparison series, okay? So sometimes you're just going to subtract those highest degrees like we did on that one. So like here, I would just use 1 over n squared. You can use the 1 over 3n squared if you want, but I would just use 1 over n squared for the comparison series on a limit comparison test. And here, I would just use like 1 over the square root of n. That's 1 over n to the 1/2, and that's a divergent p series, okay? And then right here, I would just go n squared over n to the 5th, use 1 over n cubed as that comparison series. Now, when we're doing the direct comparison, I'm just going to talk about this all at once. When I'm doing the direct comparison test, when I see this 1 over 3n squared, when you're doing a direct comparison, I'll mention this again on the next video, but you want the comparison series to look practically identical to the original one. So if I have 1 over 3n squared, if I'm doing a limit comparison test, I'm just going to do 1 over n squared. I could do 1 over 3n squared, but 1 over n squared would be just fine. If I'm doing a direct comparison test, I need to use 1 over 3n squared. I need to use that coefficient right there. And then right here, it's not always going to be a p series. You're not always going to subtract your highest exponent. So if I have like 4 to the n over 5 to the n, what I'm going to use as my comparison series is a 4/5 to the n. Because if you think about the summation of 4/5 to the n, that's an easy geometric series. And so you just want to choose your comparison series for something that's easy, that you know what that does. You know, so like going down here, I have 2 to the n over 5 to the n. So I'm going to use the summation of 2/5 to the n because that's going to be very close to that. And then we're going to be able to compare that. We're going to know that's an easy geometric series there. So sometimes if you know it's like an easy u to u in the problem, you could possibly do that. But the comparison series is almost always an easy p series, an easy geometric series. Maybe we'll squeeze in like an integral test somewhere and stuff like that. But hopefully that helps you out for that limit comparison. And watch the next one because the direct comparison goes right along with this.